Hello everyone, Mitchell here. Our exam is coming up in a few days. So today I'm going to be going over some topics to help you get prepared. I went ahead and created a poll to get some feedback on which topics are most challenging for you students. It looks like number one on the list is loop invariance. So let's go ahead and start there. I'm going to go ahead and create a simple example where I calculate the mean. So I have a list of integers here, as well as just a sum float, which I'm going to use to keep track of the total. Now let's go ahead and declare this for loop here, like so. And then just add to the sum. Okay, so that's how you calculate the mean of a list. Okay, so a loop invariant is a important piece of information that is going to hold true before each iteration of the loop and after every iteration of the loop. There's actually not just one invariant. There's going to be multiple invariants for a single loop. So an example would be 5 equals 5, right? So like I said, there will be multiple invariants, but they're going to have varying degrees of relevance. So 5 definitely equals 5 before any iteration of this loop, and 5 also still equals 5 after. So this has 0 relevance to any loop, but it is still an invariant, technically. So another one that has like a medium amount of relevance would be I is less than list.length. We can also declare these a little bit less formally by just doing I in English. So we can do I is less than list, is less than the length of the list, right? So that one is pretty self-explanatory. It doesn't have it's a whole lot of relevance, but it also is a variant, but not quite the answer we're looking for. So we wanted to think about how we can represent the value of this sum variable and how it's going to change with I. So we can go ahead and just start thinking about the first few iterations and try to create a pattern, right? So the sum of so on the first iteration, sum will just equal list of 0, right? But on the second iteration, sum is going to equal list 0 plus list of I. And then on the third iteration, oh, sorry, not list of I, list of 1. On the third iteration, it's going to be, right, it's going to be this. So we can see a general pattern here, and this is going to happen all the way up until n. So we can go ahead and summarize this in a single statement like this, right? So we can just do 1, and then we could do ... plus list of I. Great. So and then that's our invariant here. This would be the most relevant invariant, and therefore the right answer, or the answer we'd be looking for. So you can also state this in English, right? So you can say so it's a little bit confusing because sum, the variable name sum is also like the sum. So I'll do the variable name named, or I'll do the variable sum will be sum is equal to the sum of all values of a list up to I, right? And that's just the same way of saying the same thing right here. Alright, so pretty self-explanatory stuff. I'm sure you guys can figure it out. Let's go ahead and see what the next item on the list is. Okay, so calculating time complexity. Alright, so I have a made-up algorithm here And let's go ahead and calculate the complexity of it. So what is time complexity? Time complexity is basically to use to analyze how how the execution time of an algorithm changes in relation to the input size growing, right? So we want to know how the time requirements are going to change when the input gets larger and increasingly larger. And it's always going to be the worst case, right? So we want to make sure we overestimate it. We never want to create kind of like a more conservative, estimate and underestimate the time complexity. So let's go ahead and get started. So let's see here we have 3 nested for loops. The first one just runs, it runs from 1 to n squared, right? So therefore it runs n squared times. And this one is going to run, it's going to run, so this one's a little bit different, so it runs up to I, right? So it's going to run 1 all the way to n squared, right? So we can express this as a equality, just like that. But like I said, we want to do like the worst case, so it's just going to be considered n squared as well when we actually calculate it. But I'll leave that there for now, and then we'll see here. So this just is a constant here, so it runs 5 times no matter what. So we're going to see that this isn't really relevant in calculating our time complexity because, of course, this is just going to scale it, and we really want to know, we want to only have exponential changes in the time complexity in relation to size. So let's go ahead and see here. So since these are nested, we want to just multiply them. So we have n squared times, too big over here, n squared times 5. Okay, so like I said, we don't care about the constant because this is gonna like scale all the values by 5, so it's not relevant when it comes to time complexity over an expanding input set. So then we can just go ahead and simplify this to n to the 4th power. And there we go. Alright, great. So let's go ahead and move on. Can you go through how to approach a recursive problem? Sure I can. Let's do that now. So I have a recursive problem here. So there's 2 parts to any recursive problem, right? So it's the base case as well as the recursive relationship. To solve this, we want to be able to find an equation that represents the recursive relationship at any point without needing to calculate the predecessor values. For example, like if we want to find the output of t of 8, right? We need t of 4 and t of 2 to be able to calculate that value. So by solving it, we're not going to necessarily need the previous outputs. So let's go ahead and do that now. So what I would recommend starting for any type of these recursive problems is I would just find the first 3 or 4 outputs, right? So we can put in the base case. So we know the first one. The second one is just 5 plus 1, and then t of 4, which is just going to be, oops, sorry, this is 6. And that's going to be 11, and then t of 8 is going to be t of 4 plus 5, which would be 16. Alright, cool. So you can probably be able to see a pretty obvious pattern here, just being able to see this here. But we can use math to be able to solve this easily. So what we're gonna do is we're gonna start plugging in the equation into itself, and then try to see if there's any pattern or any type of relationship between the functions plugged into itself, and we're gonna do it 3 times to see if there's any pattern. So we're just gonna plug in t of n into t of n, and what that's gonna give us is it's gonna be t of n over 2 over 2, and then 3 plus 5, and then of course plus another 5. Right, so this is going to be the second one, and then so if we do t of n, like so. Oh, let's go ahead and let's go ahead and simplify this one first. So this is simplifies to n over 4 plus 10. Okay, great. So let's see this one. So this would be n over 4 over 2 plus 5 and then plus 10. It would look something like that, which of course simplifies to t of n over 8 plus 15. Okay, so we can start to see a sort of pattern here. We want to look at this and really think. So it looks like, so it's always it's n divided by a number, and it looks like it's a multiple of 2. So we want to think, so what operation can I do with 2 and 1, right? It's going to give me this value, and then how does this change when you have a 2 and instead of a 1 you give it a 2 and now it's 4? And again here, how would you change this original 2 where you would supply it a 3 and it would give you an 8? So that's just powers, right? So we can start creating the general relationship, and we're going to introduce a variable. So we know it's 2 to k. We're going to do k. And that's going to be, basically it's going to represent this value here. So if k is 1 here, and of course 2 with the exponent of 1 is just 2, and then 2 squared is 4, and then 2 cubed is 8, which makes sense. And then if we look here at the integer that's added after the recursive call, that's pretty simple here. We can see it's just a multiple 2 to 5, 5 times 1, 5 times 2, 5 times 3, so it's 5 times k. Okay, so now we have this fancy relationship here. We want to figure out how to turn it into the answer. How we're going to do that is we're going to go ahead and solve for the recursive relationship using the base case here. So what we're going to go ahead and do is we're going to set this here to, we're actually going to set it to t of 1, right, plus, because this is the base case here. This is the, I guess, first value. So we're going to set it to t of 1, and then we can use this to solve the recurrence, right? So we still have, this is a little bit closer, so we can go ahead and, so we already know t of 1, which is just 1. And then, but we still have this k here, which is 5k. So this is a problem, however, we can solve it decently easily. So since we know, since we plugged in the base case here, we can go ahead and set up this relationship. So we know n over 2 to the k exponent equals 1, which is the 1 as in this argument within the parentheses, or the input to the function. So now we can go ahead and solve this by simplifying it like so. Then we take log 2 both sides. And there we go. So we have k. Now that we have it solved, we can simply just substitute it in here. Log 2 of n. Great. So yeah, this is in fact the right answer, but we want to make sure that it's right. Let's go ahead and verify. So t of 1 is the base case, so we can set t of 2. So t of 2 will be 1 plus 5 times, so log 2 of 2 is just 1, so we 5 times 1, so we 1 plus 5, which equals 6. Oops. So that looks good. That's in line with our first results. We have t of 4, so that'd be 1 plus, so log 2 of 4 is 2, so that'd be 5 times 2, which is 1 plus 10, which equals 11. Great, so that also is the same value we have here, and then we can try finally t of 8. That would be 1 plus, and then log 2 of 8, it's just 4. Oh, sorry, that's 3. I guess 4 would be 16, but that's 3, so that would be 5 times 3. That would be 1 plus 15, which is 16. Alright, great. So that's how you solve a recursive relationship. I also am going to include some information in the description about recursive relationships that I recommend you check out. Let's go ahead and check the board. So it looks like the last item we have here is the divide and conquer algorithms. So a great resource for this, as well as the rest, all the content in the class, is LeetCode. LeetCode is a collection of programming questions that you can really easily attempt yourself and actually code. And the problems on this website cover all of the different material that'll be done in this class, and it's a great way to practice for job interviews as well. So as you can see here, they have a divide and conquer section, and also a recursion section, as well as tons of other things like heaps and binary search trees and information that will be covered in this class. So for divide and conquer, I'm going to go ahead and show you all how the majority element would work. Okay, so let's see here. So given an array of size n, find the majority element. The majority element is the element that appears more than floor n over 2 times. You may assume that the array is non-empty and the majority element always exists in the array. Alright, great. So I'm going to go ahead and use this diagramming tool. So one thing you'll see here is I have 2 small input sizes, one of even length and one of odd length. They are a little bit different just because in divide and conquer, you can't split the odd ones up right down the middle, so it's always important to consider them both. But let's go ahead and get started. So, of course, we're just going to keep on splitting up this problem in half for each level of the tree. Okay, yeah, it's gonna be size 1 in here. Okay. Alright, so it's important to consider our base case, right? So if we have just 2 arrays of size 1, right, the majority element in each of these arrays are just going to be their own element. So if we run both of these, so the combined step is going to be the most important part. It's going to be where we actually calculate the solution. Okay, so let's move this a little bit. So when we go to combine these, so these are the same, so we can just return 2. So we know that's the majority element between both of these. So the majority element between these two are actually going to be different, right? So we're going to kind of have a tie here. And how we're going to do that is we're going to search like the right half of the array and check the counts of both of these. So since only size 2 here, we only have 1, 3, and we have 1, 2, so it's a tie. So it could actually return either value here depending on what's the default one when it's a tie. It could either be the left or the right one. So let's do 3 though, just in case. Okay, and then now when we go back to this merge step, so we have two majority elements here. We have 2 and 3. So an easy way to go ahead and now do this is we just gonna loop through the array, the original array, and then count how many 2s there are, then count how many 3s there are. And then in the combine step, we'll be able to decide a winner, which will be 2. So let's go and do the same thing here with the odd length array. This is going to be 2 and 2 and 3. And then 2 and 5. And we're going to split it up again. Like so. Okay, this is going to be arrays of 2 and 2, and then this is going to be the base case, which is just, of course, a length of 1. And then same goes for here. Okay, and then we need to continue to divide this up. Okay, great. So since this is just a length of 1, so we're gonna pass this right through. Like so. Now we can go about merging them together. Alright, so actually we can merge this here and then pass the result through later. Like so, okay. So here we have 2 and 5, right? So there's no way to tell what the majority element here is here. So it could be the 2 or 5, but since 2 is the majority element, I'm going to have us return 5. So we can tell here we have 2 2s. So when we merge these, they will be the same. So we're going to go ahead and return 2 here. And of course bring that down, but then we're gonna now we're going to merge the two and the 3. Okay, so the way we figure out a tiebreaker between these two, right, is we'll just go ahead and count how many 2s there are in this array and how many 3s there are. So we can go ahead and, it's obvious to see that there's more 2s. So when we merge these, we're just going to result with a 2. Okay. And of course this is just going to go right down. Like so. Okay. And now we can go ahead and finally. Oops, that'll be 5. Now we can merge the 2 for the final solution. So we have 2 and 5. So to decide a tiebreaker, we just count the amount of 2s in this subarray, which is 2, and the amount of 5s here, which is just 1. So we have a clear winner here, and we can combine them for a solution. Alright, so I'm sure you may have a lot of questions about how I came to this conclusion. I'd recommend, if you do, I'd recommend just opening up this problem, maybe giving it a crack, but you can go here to solution and scroll down, and you can see the divide and conquer solution here. And it goes ahead and explains it. Alright, so I think that's it. Please let me know if you have any additional questions. Keep in mind, I am a TA, right? I haven't seen the test, so I'm just giving you what I think is going to be best. I hope it helps. I think you guys will all do great. It's also done on a curve, right? So if you get a 60%, it may not be all that bad. But try your best and make sure to study, and you'll do great. Good luck, everyone.